I work at Intel for about 6 years now, and 5 of those years I've been working on PMDK, which is a suite of libraries and tools for persistent memory. And today I'm going to be talking about what are the lessons that I and my team have learned throughout that time. But before we begin, I wanted to give a brief overview of what actually is PMDK. So PMDK is, like I said before, a suite of libraries and tools for persistent memory. So we divide those tools into two different use cases. We have tools and libraries for persistent use cases where you care about persistence of your data, and we also have volatile libraries that can be used if you just want to take advantage of larger capacities of persistent memory, not necessarily the persistence of it. On this talk, I'm going to be focusing on the persistent libraries, and more specifically on libpmem, libpmfj, and libpmkb, because those are the most interesting ones from broader perspective. Okay, so I have quite a lot of slides, and we don't have much time, so I'm going to be going through the slides very quickly. So if you have any questions, just ask them right now instead of waiting. I think that's going to create a better discussion. The first topic I'm going to be talking about is the usability aspects of persistent memory. So throughout the years, we went through a couple of different iterations of our API in libpmfj case. This is how the first iteration looked like. So the programming language that we use is for this library was C, and I dug that out of some branch of a fork on my GitHub page, and this is what we started experimenting with when we first tried to come up with a sensible programming model for persistent memory. So this can look similar to papers like Mnemosine or NV heaps, because that's what we based our work on. So this is an example of a linked list insert where we begin a transaction and then create an allocation and then modify a couple of values in persistent memory. To implement a transaction in C, we used set jump and long jumps, which I'm guessing for most people are arcane magic. So that's one of the aspects I don't like about this API. And some people might say this API is ugly, which is a reference to the previous talk on previous keynote. But we try to improve on that. So it took us a while, but eventually for C we released something like this, which is less verbose. So you have to write less code, and there is you no longer have to deal with all of the details of implementing a transaction, but you can just focus on the code. This still could be considered ugly because there are a lot of different macros that have to be used to instrument the transaction. And if you do forget to use one of those macros, especially the snapshotting ones, then you are going to have a consistency problem. I'm going to be talking about how to detect those consistency problems later. So this API also required a use of macros for types, because in the previous example, you might have noticed that the types no longer had any type associated with them. So each node was effectively a void pointer, which is not convenient to use. So we tried to improve on that, and we introduced a notion of typed object identifiers, which is a very, very fancy macro that tries to be a smart pointer in C. Again, this is, we were constrained by the programming language that we use. So I think we did the best we could with that. So we realized that the PMDK API is error-prone and not that easy to use. It required manual instrumentalization, it required to have fancy types and stuff like that. So we tried to improve on that with a different programming language. So we chose C++ because that's an obvious step up from C. And in this approach, we try to leverage the meta-programming facilities of C++, and we used smart pointers similar to shared pointers and closures to implement a sensible approach that focused the modifications of persistent applications on the type system instead of the code. So if you were to remove, okay, I don't have a way to point, but if you were to remove the transaction from this code, this will just replace make persistent with make shared, for example, or make unique. Then this code will normally work as a volatile application, and all of the changes really are in the types. So instead of having a shared pointer or a unique pointer in here, we have a persistent pointer. Also, instead of having a standard string, we have our own implementation of a persistent string. So we think that this is the most ergonomic approach that you can have without having to come up with some pre-processing scheme or actually modifying the compiler. And we found that standard committees are not very receptive to some difficult changes. Yep.
But it means then you can no longer link with a pure C application?
You can. So this is a normal, we didn't modify a compiler. So this is a normal C++ library that you can use this alongside your normal volatile data structures. And for example, so in this example, I have in linked list insert, I have a standard string, and then I assign it to a persistent string. This works because we implemented a constructor in the string from the standard string, right? And we do that for other data structures as well.
So, but if I have a pure C application, I won't have access to the STD type, right? So
yes.
It's
So
not different from the previous version.
yes. So if I were to simply replace the STD string with char star, so a character array, then this assignment will also work because we also have a constructor from char array.
So for a pure C application, just use the C. You wouldn't use C++ library.
Well, I'm assuming that the previous version of the library is no longer valid.
It is valid.
Oh, they both?
Yeah.
Oh, okay. Sorry.
It's just that
I thought this was the new
in C++,
updated
we
version.
had the type system to work with to make it so much cleaner.
Well, I agree.
In C, we did.
Fine.
Yeah.
They're both validated.
Okay.
Yeah, they are both. Go ahead.
Yeah. What's the lock? The VP lock?
So this is a way to show in this example how to synchronize data structures in concurrent applications. So in this case, the lock is a simple PMDK mutex. We could theoretically you can use a volatile mutex. That's not a problem. But then you have a problem. What happens if you crash with the mutex locked? You will have to reinitialize array locks. So PMDK mutex is just something that improves on that and automatically releases your resources when the mutex is encountered for this time. Okay, done.
So the transaction commits when it goes out of scope.
Yes.
Can you also support like linking multiple operations into one transaction? Like, say, I want to do 5 list inserts and then commit at the end of the 5.
Yeah.
Okay. I mean, would you call linked list insert 5 times and pass it into context ID or something? Or?
No. The way this would work is you can have an outer function that also has a transaction, and then simply calls this function 5 times. This will cause the transaction to be nested. This transaction will be nested. So all of those 5 operations will be executed in the context of the outer transaction.
Okay, so if you and transaction hit each other, it automatically figures out it's nested and won't commit until
Yeah.
the property.
So the transaction context is thread local internally. So this function actually starts, calls PMDK text begin, and inside of that function, we have a TLS variable that stores the context of the transaction.
You have something called a persistent pointer. Is that a shared pointer, or is it just something that points to persistent data?
It's a smart pointer that just points to persistent objects. It's an offset pointer.
Okay.
You have a question?
I may ask you after you know.
Okay.
Yes.
The transaction is just in terms of persistence or also in terms of usability?
This is just in terms of persistence, but we get that question often. So LPMJ does not implement STM kind of functionalities. So it's not, it doesn't provide you with any concurrency protections. All we really do is allow the transaction to accept locks, so that you can manually instrument do your own locking scheme. Right? Doing lock-free programming using this API is difficult. Right?
One more question about the nested transactions. So if I use the same lock for all of them, does it notice that I already have it held?
Yep.
So your POP is a memory pool, each of which has a root pointer?
Yes.
Okay, so that auto BP line, that's using the root pointer to find the head of the linked list, or the base of the linked list, right?
Yeah.
I don't understand what's happening if there's already stuff on the list, because new OID next is null pointer. Shouldn't that be set to the contents of the existing list if you're inserting at the head?
Yeah. That's a mistake I made. Sorry.
Just checking. So you just leaked the rest of the list, right?
Yes, I can make that change, but in my previous examples, I have.
Right. Better.
We wanted the example to be real.
In real life.
He just wanted to make sure you were paying attention. Good job.
Bugs in real life.
Yeah. Okay, so this was just to show you the progression that we've had throughout the years, right? So we started with a relatively ugly and bad API, and we got to the point where I think this is pretty much usable in normal applications. So the lessons that we had from this is that we released too early our version of FlippyMJ, way before there was any hardware, because we wanted to kind of get ahead to make sure that this is available. But I think that that might have been a little bit of a mistake, because there were some changes that we've made later on that were difficult because we committed to maintaining a stable API and stable on-media layout. Because remember, LPMJ is effectively a file system, kinda, where we have to if we release something, then we have to maintain backward compatibility, or at least provide a way to upgrade your applications. So that creates a significant challenge for us. So I think one of the best approaches you could take of modifying or existing applications to take advantage of persistent memory is through the type system. I think it's way easier to just add type qualifiers to objects, to pointers, instead of instrumenting large parts of volatile application. Right? This is one of the ugly parts of LPMJ in C, that you pretty much have to rewrite your code, right? Because it's so much different. And I think eventually we will have to take advantage of modern programming languages. Like we used C++ because that was the most logical choice because it's commonly used. But honestly, I think languages like Rust or Scala are also very cool in that they allow, they have very strong meta-programming capabilities that we could take advantage of. Okay, so the next thing I want to talk about is the applications that do not actually want to make anything custom or custom data structures. Because libpmobj is really aimed at applications that want to make a custom data structure, or they want to really have the lowest possible latency on their operations. But we also discovered that a lot of people don't really actually need that much of flexibility, and they just want a simple interface that they can take and use as they did. So we decided to implement a simple key value store that had a very, very familiar interface, so that people could have a smaller learning curve and adoption curve in taking advantage of persistent memory. So I think the lesson in here is that it's better the devil you know than the devil you don't, because libpmobj introduces, or any kind of really persistent memory programming model introduces a lot of complexity. And if we provide something that's actually familiar and pretty much exactly the same as existing utilities, but that are optimized for persistent memory, then we can really make adoption easier. Okay, so this is one of the things that I spent a lot of time on. So I'm the author of the persistent memory allocator in libpmobj, and I don't really like it because fundamentally the allocation interface makes sense because it's familiar, right? This is the way you allocate. This is allocating this way, like in the example, is the way people did it for years. And that makes sense, right? We want to be familiar. But the problem with this, with the dynamic memory allocation on memory mapped files, is that we no longer get the same facilities that the operating system provides to combat fragmentation, right? We no longer can easily take advantage of virtual paging and all of that good stuff. I think this is an unsolved problem right now. I also think that there might be a better approach than having a simple malloc interface, similar to malloc interface for persistent memory. And the most significant reason for that is fragmentation, right? Because we expect persistent heaps to be long-lived. So you can imagine to have a persistent heap that lasts for years, even. And if you had ever run any long-running application, like if you had a Redis instance that ran for months, then you know that the fragmentation adds up. So you have to deal with it somehow. In Redis, for example, they had implemented their own defragmentation scheme, where they simply call realloc if the page, if there is a better placement for an object, and that takes time and can be difficult to implement. So a different way to combat this problem is through compaction algorithms, or compacting garbage collection, which is cool, but I think for terabyte-sized heaps that persistent memory allows for, this might be very challenging. I haven't seen a real-life garbage collector that actually works on terabyte-sized heaps. I think Oracle has something, but I haven't tested.
There are garbage collectors that do region-based management that collect the regions that have the least amount of objects in them, relocate them to compacting regions, but they don't have to do the whole thing. So
I know.
there is a way to sort of get around that problem of garbage collecting the world.
Yeah, I guess so, but I haven't tested that in practice, and I think this is an open area for research, honestly.
Isn't the reason you can do that because you're in Java, which is a managed language?
Well, yeah, the thing is, well, you can do garbage collection because you know what's a pointer, you know what's the reference.
Right.
So it requires you to have an object model where you actually understand the structure and the layout of the data in the garbage collection.
Yeah.
Using general application programming, it's not a problem. There is actually a C garbage collector, the Burn Mill, but it was a non-deterministic collector. It made a guess about certain things.
Yeah, I think it assumed that eight bytes can have a pointer, right? It iterated through the entire.
So having a managed language, managed runtime means that you know the organization of data.
Yeah.
And that's really critical for doing problem garbage.
Yeah, I think.
But the region thing is a separate thing because if you can garbage collect, if you have a region-based model for the storage model, you can basically only do partial collections and not have to collect the whole world.
Yeah.
So
I agree.
it gets around the problem of having a massive heap and having to suddenly bring everything to a halt.
I think you had a question.
Well, I think it's already been covered. In order to relocate objects, one must somehow ensure that there isn't a pointer somewhere out there in the application pointing into the thing you're about to move.
Yeah. So it's in C and C++, that's extremely difficult to implement. In managed languages, it gets easier.
So do you not have a file system that's providing you virtualization layer between the virtual memory addresses and the physical memory addresses?
There is,
So that you have a really large file, a very sparse file, and you punch holes in the file.
yeah. So this is actually the first point I had, where technically speaking, you can implement a scheme where you defragment the heap by punching holes in the virtual address space and just kind of reallocate, move pages around. But that has two problems. The first problem is that will require 4 kilobytes pages, which for terabyte heaps might not be an ideal solution because when you get to 2 megabyte pages, that's no longer useful. I mean, the heap can get fragmented on objects that are very, very small, right?
We have slab allocator out there for that. You get lots of allocators that pack small objects together in size.
Yes, but still, that creates fragmentation, right? That there is no silver bullet that works for every single workload, and so I've seen one research paper about using virtual memory as a way to defragment the heap, and it did use segregated feed algorithm. And in LPMDK, we also use segregated feed algorithm that does what you say, like we allocate small objects together, right? And theoretically, there might be no holes in those smaller regions. But the simple case where you just allocate, for example, 1 kilobyte, then free every other object, and then you can no longer allocate 2 kilobytes. That's unsolvable, right? You could theoretically solve that. No, I don't think you could solve that for small objects using this method, right? And that's one problem with 4 kilobyte pages. And then I think eventually this will just make so that no 4 kilobyte pages are ever contiguous, which I think also can be a problem because then we can never take advantage of huge pages, which again makes the problem bigger. And for larger heaps, this makes the TLB work out harder. Okay.
I'm the invisible guy. I remember in 1980 going to a talk at Digital Researchers Lab at Palo Alto. A guy named Joel Bartlett, who had this plan for an allocator that could find dead processes, find the stuff that was allocated from them and move it around or collect it and do defragmentation. And I don't think anything is advanced very much from that point. I just have a feeling like this, we're not going to make advances in this area. Am I wrong?
So I haven't researched garbage collection all that much, but in C applications, so I'm not sure why you are referencing multiple processes, because right now, if you have a new process, then for volatile memory, you have a clean slate. For persistent memory, you obviously start with some heap that has some objects.
Back then, they were trying to do sharing across multiple processes per shared
Okay. So the problem there is the fact that in C and C++, we really have offset pointers, right? And to do what you're saying, so the garbage collection, we will have to have some kind of logical way to move objects around. So we can do that in Java or Go or whatever, and not in normal languages. But I think there is a lot of progress on garbage collection in general. So yeah, I think there is a lot of work going on around garbage collection of large heaps. So I think that's going to be the key. I think eventually persistent memory programming models will have to be compacted or garbage collected in managed language that has a garbage collector that can handle very, very large heaps, terabyte-sized heaps. I think that's the ultimate solution, but I don't think we are there yet.
So you're talking about going to higher level languages. What about you actually push down garbage collection in the hardware? What does Intel hardware people think about?
I don't think that's possible. So we can, like we discussed, we can garbage collect or defragment based on virtual memory, but that's constrained by the size of the page, right? And the smallest page on IX6 is 4 kilobytes. And if you have small objects, and applications tend to have a lot of small objects, then the fragmentation on 4 kilobyte page doesn't really help much.
No, yeah, I agree that there will be fragmentation. Exactly. The question is how efficiently we can do the compaction, or how efficiently we can do the garbage collection. And if it's for terabytes of memory, those on the software would be really have way high overhead.
Yeah. Okay. So I think we could, technically speaking, have an accelerator that did DMA compaction so that objects are moved around, but that still doesn't solve the problem of having the pointers be fixed in place. We could move objects around using DMA on some accelerator, but still we will have to have a way to say to the application that this object moved, or the application itself will have to initiate a DMA to move that object. But then, again, in C or C++ or non-managed languages, it's just difficult to do.
I mean, it's like rare leveling of steroids.
Yeah. Okay, I don't have much time, but so we went through about half of my presentation. So I'm going to just finish the next 2 slides, and I think we can open to questions. So another problem that we encounter is maintaining consistency in the presence of failures. So ever since we started working on the PMDK, we realized that it's not going to be easy designing an algorithm that is going to be fail-safe, right? And it's going to be always consistent no matter where we interrupt it and no matter how the CPU reorders the buffers. So to alleviate those problems, we created tools that help us. So we did two tools. We created PMCheck, which verifies if all of the memory was flushed to persistence correctly. And then we created another tool that checks if our invariants about data structures are correct, are always maintained. When we implemented PM reorder for the first time a couple of years back, we actually found a problem in our transactional unlock implementation. So it was definitely worthwhile to do that. So the lesson here is that persistent programming is hard. And I acknowledge there might be some approaches that make it easier, but to get most performance, I think this type of programming model is necessary, and unfortunately, this programming model is difficult to do. So I think that testing through killing an application or just pulling the plug on a server isn't an ideal test. It's undeterministic, which means that it's difficult to debug. So this is one of the reasons why we actually implemented software tools that kind of virtually allow us to pull the plug on a server at every single moment of time in the application. So this way we can deterministically check if our algorithms are actually consistent, no matter when we will tell the power will go down or the application crashed. Yeah, I think that wraps it up.
Any last question before we? I know we're kind of tight on time.
Yeah.
You said that was half of your slides.
Yes.
By any chance, could finish your talk at the end of the lunch break? I mean, this is super interesting, and I would love to see the rest.
Can you talk with your mouth full?
Well, we'll publish the slides.
Yeah, we will publish the slides.
So I think that'll help. But of course, you guys can just talk.
Yeah, well, if anyone is interested, I think I can do that.
And I agree. I've seen that. I previewed the slides, and the whole talk is actually pretty interesting. These half-hour slots are kind of too tight, I think.
Regarding testing, can we agree? I actually advocate. I did this yesterday. I advocate for whole system power interruption testing. It's not sufficient, but I think it's necessary. Can we agree that the testing you described plus whole system power interruption is a good thing to test?
Yes.
Okay. Yeah, go ahead.
Sorry, just
let's squeeze one in.
follow-up comment.
Yeah.
I think a really easy way to do that after we heard the VMware talk yesterday, if you can test in a VM, you can pause the VM, use introspection from the hypervisor to see what state your application is in, and then kill it for real.
That's a very good idea. We did.
Except killing the VM doesn't stop you from like hitting the EQ flash and all the other hardware.
That's right. The stuff in the cache is still there. What you really want is a test where the things that haven't been flushed from the cache vanish.
Yeah, that's what you want.
And that is a trick, and I know that you worked on that too.
And VMs can snoop, which is hard.
Yeah, it's a pretty interesting problem. So we really should move on though, because I want to make sure we get through all three talks. Thanks.
Thanks.